Good morning, good afternoon, and good evening, everyone, and welcome. I'm Stuart Neal. I'm the Director of Strategy and Communications here at the International Chamber of Shipping, and I'm delighted to welcome you to this briefing session on the recently approved IMO guidelines on the reduction of underwater radiated noise. So just to let you know, this session will be recorded and made available to all of you after the meeting. And we encourage everyone to participate by asking questions in the chat function in the system that in the control panel that you have. Fortunately for you, you're not relying on me as the expert. We have a great panel with us. So firstly, I'm delighted to welcome Captain Dr. Vahid Vahili. So Vahid holds the position currently as the Research Fellow at the Department of Civil, Maritime and Environmental Engineering at the University of Southampton, where his primary research centers on the sustainability of shipping. Specifically, he places strong emphasis on energy and zero emissions within the maritime industries, including ships, ports, and shipyards. So welcome, Vahili. Great to speak to you. And joining him on this panel today is my colleague, Chris Waddington, who's the Technical Director here at the International Chamber of Shipping, where he leads on the work of the development and implementation of policy work related to technical and operational environmental regulatory risk for international shipping. He actively participates in IMO committees, including the work around underwater radiated noise and with other industry associations. So welcome, Chris. So ladies and gentlemen, hopefully you're going to be in for a good discussion. Please, as we say, remember to put your comments into the chat as you hear. We're going to kick off with Chris going through why we need to be interested in underwater radiated noise and hopefully provide a summary of what these revised IMO guidelines mean for all of you. So Chris, can I hand over to you to kick off, please?
Thanks, Stuart. And next slide, please, Richard. Okay, so good day to all and thank you for joining our webinar today. The objective of my presentation is to raise awareness of IMO's revised guidelines on the reduction of underwater radiated noise, or more commonly known as URN, and to encourage the uptake of the guidelines. I'll talk about why it's necessary to reduce URN and will provide a summary of the guidelines. I'll also discuss the strong synergies between most fuel efficiency measures and URN reduction. This aspect represents a great opportunity for ships to readily reduce their URN emissions while simultaneously achieving compliance with the IMO greenhouse gas regulations. Next slide. So let's firstly consider the reasons why it's necessary to reduce URN from shipping. The ability of marine life to hear can be impeded by the URN generated by shipping. And as can be seen from this graphic, the spectrum of sound attributable to shipping closely aligns to the frequency ranges used by fish and marine mammals. Environmentalists and scientists have in recent years become increasingly concerned that excessive levels of background URN can impact on marine life by reducing communication, leading to changes in social behavior, damaging hearing, reducing hunting and reproductive performance, increasing stress, and changing migratory routes. And to use an analogy, it's difficult for humans to communicate effectively when we experience noisy road traffic. And for marine life, URN generated by shipping is having a similar effect. Next slide. To further illustrate the impact on marine life, I'd like to draw a comparison between the acoustic communication of fish and the typical URN emitted by a ship. For example, the mating call of a codfish is a faint grunt produced by its swim bladder, whereas the URN produced by a ship is dominated by the loud fizzling popping noise of the propeller cavitation. For sound measurement in water, it's normal to compare noise levels at a distance of 1 meter. And for the codfish, this is about 127 decibels. whereas for a container ship, it's typically 175 to 195 decibels. Although it should be noted that decibels are recorded on a non-linear logarithmic scale, and therefore the difference in sound level between the fish and the ship is much greater than the numbers suggest. It should also be noted that URN can travel significant distances. For example, 100 Hz may be detectable after propagating hundreds or thousands of kilometers, and 100 kHz after a few kilometers. Hence, the noise from geographically distant ships can combine to produce an ambient level of URN that can adversely impact marine life by masking communication. Next slide. This graph is taken from a 1995 study and plots ambient URN levels within the oceans against year. For example, for the West Atlantic over the period 1950 to 1980, ambient sound increased from about 70 decibels to 85 decibels. And overall, the study concluded that globally, from 1950 to 1980, ambient ocean noise levels rose by about half a decibel per year. Advocates of URN reduction have suggested that this trend is likely to continue, and for some regions there is evidence to support this view. However, recent analysis of deep ocean sound measurements by Pennsylvania State University and the UK's National Physical Laboratory have indicated that this is not a universal trend, with some regions recently seeing static or reducing levels of URN. Some scientists have postulated that fuel efficiency measures, for example, speed reduction, could be contributing to such URN reductions, and others have suggested that natural phenomena may be the cause. Next slide. Turning now to IMO's URN reduction guidelines, these were first adopted in 2014 as Circular MEPC1 Circ 833. Take-up by the industry was low, and this, coupled with concerns over the impact of increasing URN, led to the revision of the guidelines, and this process was completed in January this year. In July this year, the new version was approved by IMO's Marine Environment Protection Committee as Circular MEPC1 Circ 906. And via the IMO Docs website, the guidelines are now freely available to anyone that has registered for a public account. And after this webinar, ICS will also circulate a copy of the new guidelines to all registered attendees. Next slide. Key features of the new guidelines are as follows. They apply to new and existing ships. They are non-mandatory with no specified reduction limits. Ship noise signatures are initially baselined by measurement or prediction, and a noise management plan can be developed by the ship owner. They include suggestions for incentivizing uptake, for example, using reduced port use, and they are currently within a 3-year experience building phase. And the following slides detail the key aspects of the new guidelines. Next slide. The biggest change relative to the previous guidelines is the introduction of the noise management plan. This is intended to be a flexible tool that allows a ship owner to take a customized approach and may define design changes or ship modifications or operational enhancements intended to reduce URN. Templates for a simple and a detailed version of this are provided within the guidelines. The simple version includes a statement of the objective of the plan, details of the approach to be taken, for example, with respect to the measurement of noise and the practical measures to reduce noise, and details of how the ship owner will monitor and evaluate the success of his or her actions. The more detailed version also includes details of how a ship's noise signature will be baselined and targets for URN reduction. For example, reduction relative to the baseline signature. Next slide. For a new ship, the noise management plan should be developed at the earliest possible design stage. As far as reasonable and practical, a plan can also be developed for an existing ship. As well as the ship owner, the development and implementation of plans can be supported by ship designers, builders, ship operators, flag administrations, class societies, and equipment suppliers. During the development of the plan, the interrelationship between energy efficiency measures should be considered, and energy efficiency will normally take precedence. However, the majority of energy efficiency measures reduce URN, and with careful planning, it is possible to comply with the greenhouse gas regulations whilst also reducing URN. Next slide. The baseline noise signature of a ship may be included within the noise management plan. Baselining may be achieved by measurement, model tests, or numerical prediction, and the guidelines include lists of suitable techniques. The noise management plan should give an overview of how the baselining will be achieved, and the baselining should reflect the ship's normal operational conditions and speed. Next slide. Within the guidelines, there are no specified noise reduction targets, and ship owners may define their own. There are a number of quiet ship notations offered by class societies, and these are listed within the guidelines. A ship owner may choose to procure or modify a ship to gain such a notation. Alternatively, the target URN level from such class rules could be adopted within a noise management plan. A noise management plan may also define a progressive noise reduction strategy whereby target reductions are gradually tightened. And for ships that restrict their operation to a particular locality, local sound propagation conditions and sensitivity of local marine life may also be considered when setting targets. Next slide. So here is an example of noise reduction targets that apply to Det North Veritas's silent notation. And in the transit condition and at the low frequency end of the spectrum, the target level is 178 decibels. And at the high frequency end of the spectrum, the target level is 145 decibels. For comparison, and as previously mentioned, the broad spectrum sound level for an existing container ship is typically 175 to 195 decibels. Next slide. The guidelines propose ways that stakeholders could incentivize the reduction of URN. For example, maritime authorities, financial and insurance institutions, and others are encouraged to establish schemes to support noise reduction efforts. The incentivization could be based on relevant URN ship class notations and/or recognition of a noise management plan, URN reduction targets, quiet ship and engine technologies, and appropriate maintenance or speed reduction programs, etc. Examples of incentives are the application of discounted port dues and fairway fees, and a few schemes are already in place. For example, the ports of Vancouver and Prince Rupert both offer port tax reductions for improved URN. According to Bureau Veritas, a large container ship with URN reduction measures in place could earn about 4,000 Canadian dollars per visit. The Port of Helsinki also offers an environmental discount of up to 10% on vessel fees, which could in principle apply to URN reduction. Next slide. Many of the fuel efficiency measures adopted by ship owners to meet the greenhouse gas regulatory requirements are also known to reduce URN. And IMO regards this interrelationship as worthy of investigation and has arranged an expert workshop to further consider this aspect on the 18th and 19th of September. If considered at the same time as fuel efficiency measures, it is likely that significant URN reductions can also be achieved at little additional cost. Next slide, please. This table provides a few examples of fuel efficiency measures that also reduce URN, and all figures are approximate. However, it is apparent that some of the commonly adopted fuel efficiency measures can individually lead to URN reductions of the order of 10 decibels. I've come across very few fuel efficiency measures that increase noise, and the only ones I am aware of are the optimization of the propeller blade area ratio and speed reduction of ships equipped with controllable pitch propellers. Hence, if care is taken during the development of ship designs and operational procedures, compliance with the IMO greenhouse gas regulations can be ensured whilst also achieving beneficial URN reduction at minimal additional cost. Speed reduction can also significantly reduce URN, as it reduces propeller cavitation. Indeed, if speed reduces enough, the propeller will drop below the cavitation inception speed, and the cavitation, which is the biggest source of URN, is eliminated. For comparison, in 2015, Maersk modified 11 of its G-class container ships, principally to improve fuel efficiency. The modifications included replacement of the bulbous bow, derating the main engines for slow steaming, and installing propeller boss cap fins to reduce cavitation. For 5 of the vessels, URN measurements were made before and after the refits, and sound reductions of 6 to 8 decibels were recorded. Next slide. So, in conclusion, URN adversely affects marine life by hampering acoustic communication, and this has environmental and economic impacts. As one of the major sources of anthropogenic URN, our industry has the opportunity to play a significant role in controlling URN. The revised IMO guidelines on URN reduction are available now and provide ship owners and other stakeholders a flexible and pragmatic approach. Many of the measures that ship owners are increasingly adopting to comply with the IMO greenhouse gas regulations will also reduce URN. Therefore, if care is taken during ship design and operation, compliance with the IMO greenhouse gas regulations can be ensured whilst readily achieving beneficial URN reduction at minimal additional cost. Through the 3-year experience building phase, ICS would welcome the feedback of ship owners that have used the new guidelines. If proved effective and a good uptake can be confirmed, the need for additional measures or hard enforcement may be allayed. Next slide. So thank you very much for your attention, and later in the webinar I'd be happy to take any questions. And back to you, Stuart. Thank you.
Thanks Chris, and thanks for a very comprehensive outlook on not only the why we need to be looking at this, but also the regulatory process that's been going through the IMO, so we understand the sort of why elements and what it is, and also the opportunity of the synergies. And I think now I want to turn to Vahid, because I think you've been looking at the sort of the practical solutions. What is it that we can do to meet those challenges that have been set out and deliver opportunities, and what are the pluses and minuses? So let me hand over to you, to Vahid, and take us through.
Yeah, thank you very much, Stuart, and thanks to Chris for his nice presentation, and good day to everyone from sunny Southampton. I'm going to share my screen. I'm just wondering, can you see my screen now?
Yes, all good.
Okay, great. Yep. In continuation with Chris' presentation, I will talk about reduction of underwater radiation noise from commercial vessel and its interaction with energy efficiency measures on board vessel. First, I will talk about source of underwater radiation noise from commercial vessel. In continue, we will talk about investigating the technical and operational actions to mitigate underwater radiation noise from commercial vessels. The transdisciplinary approach to development of underwater radiation noise management plan will be discussed. There are 3 main sources for underwater radiation noise from commercial vessels. The most dominant source of underwater radiation noise after reaching to cavitation inception speed is propeller, Machinery is the dominant source, while the speed is less than cavitation inception speed, and hull form is another source of underwater radiation noise. The most dominant source of underwater radiation noise is propeller cavitation that contributes 80 to 85% of ship's radiation noise. There are 5 principal causes of noise propagation from propeller, including the displacement of water by the propeller blade profile, the friction differential between the suction and pressure surface of the propeller, the flow over the propeller blade surface, the fluctuation of cavity volumes around the blades due to variable wake applied to the propeller, and the sudden bursting of cavitation bubbles. The propeller noise can be categorized into non-cavitation noise and cavitation noise, with the first 3 factors being ever present regardless of cavitation condition. The machinery noise is another source of underwater noise, and it means origins are from propulsion machinery and auxiliary engines. It is the dominant source of underwater radiation noise when vessel speed is less than cavitation inception speed, with frequency of less than 100 Hz. The machinery noise depends on machinery and engine room design for both propulsion and auxiliary machineries, power and rotation rate, and the way of machinery installation. The hull is another source of noise propagation. Underwater noise from the hull has 2 sources: vibration and noise of the machinery and rotating components on board the ship that transfers energy to the ship's hull and radiates into the sea, and various pressure applied to the hull because of various types of cavitation on ship's hull. Based on the revised version of guideline and considering the proposed measures and application in the document, to meet the goals and targets that have been developed at Underwater Radiation Noise Management Plan, the following categorization can be taken into consideration in Underwater Radiation Noise Management Plan. It contains 2 main disciplines, that is technical and operational, and of course combination of both disciplines can be taken into consideration. The disciplines consider the applications that can mitigate air emissions from shipping and also reduce underwater radiation noise from commercial vessels. The technical pillar is categorized into 3 subcategories, namely optimization of the propeller and its interaction with ship's hull, machinery and engine room design, and computational modeling. And operational measures are divided to ship's hull and propeller cleaning and maintenance, just-in-time and ship's speed, optimization of ship's handling, passage planning, power demand, weather routing, and convoy. Optimization of propeller and its interaction with ship's hull are divided to propeller and hull design, propulsion improving device and energy saving device, air lubrication system, alternative propulsion types, wind propulsion system, and fuel cell battery and hybrid. And machinery and engine room design is categorized to proper design and layout of machinery, low noise machinery, and resilient mounting. Computational models aid cost-effective decisions for optimization ship design and construction. The types of computational models that can optimize ship design and help in reduction of underwater noise are flow characteristics, which is including computational fluid dynamic, noise radiation, including finite element analysis, boundary element method and statistical energy analysis, and noise propagation. In addition, empirical and semi-empirical models scale tests are helpful for optimization of ship design and technical reduction of underwater radiation noise from commercial vessels. Early optimization offers cost-effective benefits, boosting energy efficiency and noise reduction. Consider that by only 1% increase in building costs, 10 decibel noise reduction is possible, and this can be reached 20 to 40 decibel by only 10 to 15% increase in construction costs. Although some solutions may comprise efficiency and energy standards, there is synergy between improvement of energy efficiency and reduction of underwater noise from commercial vessels. Proper design of propellers and its interaction with ship's hull is an important factor to improve both efficiency and reduce underwater radiation noise. High scoop propeller, forward scoop propeller, contracted and loaded tip propeller, coupled propeller, potted propulsion and azimuth propulsion can improve efficiency and increase cavitation inception speed and reduce underwater noise from commercial vessels. Innovation on material for manufacturing propeller can also affect in improving efficiency and reduce underwater noise. As an example, composite propeller. It is lighter compared to conventional propeller. However, it is anticipated to be more expensive. It has capacity to reduce underwater radiation noise across all frequency up to 5%. Around 6,400 ships use energy-saving devices and propulsion-improving devices. Propulsion-improving devices and energy-saving devices are other measures that can reduce underwater noise and also improve energy efficiency. Some examples are proper boost cap fin, proper cap turbine, pre-store stator, and maybe stock. They have the potential to decrease emission and improve efficiency up to 10%, can effectively reduce underwater radiation noise 5 to 10 decibel. The typical payback period is estimated to be around 4 to 24 months, depends on type of technology and amount of the fuel saving. Hull air lubrication by introducing air bubble curtain below the ship's hull reduce the resistance and enhance efficiency between 5 to 15%. It can also reduce underwater noise by 10 decibel. There are 575 ships with hybrid battery propulsion. For the total of 1,046 alternative fuel ships on order, there are 417 ships with hybrid battery propulsion. It can be noticed that the proportion of hybrid battery propulsion system is increasing. Fuel cell, battery, and hybridization of ship can enhance energy efficiency, reduce emissions. However, it needs additional space and introduce additional weight to the vessel. There is potential to reduce underwater radiation noise by more than 10 decibel across all frequencies. Wind propulsion system plays a crucial role to accelerate decarbonization of the industry, and using the technology is predicted to uptake in the next decade. This achieved by decreasing the required thrust and load from engine. It can enhance efficiency 5 to 30%, depends on type, size, number of technology, and the related vessel. It requires more complex design and additional effort in terms of both vessel design and construction in compared with conventional ones. The payback period depends on type, size, and number of technology and the related vessel as well. However, compare the cost difference between conventional fuels and carbon neutral fuels, it can be considered a cost-effective measure to reduce emissions. The machinery noise is the most prominent one at the lowest speed. The main engine and diesel generators are the main source of machinery noise. The proper layout of machinery can improve efficiency and reduce noise. Proper location of machinery on the center line of ship and optimization of foundation should not be underestimated in reducing vibration and underwater noise radiation. If the machinery manufacturers provide information on the airborne sound levels of the machinery, better design, technology, and a strategy for mitigation of underwater radiation noise can be considered. Taking this into account, hull resonance due to machinery vibration can be minimized and underwater noise propagation reduced by improving the hull configuration, such as surrounding the machinery area with freshwater tank, ballast tank, coffer dam, or double hulling the area. It is crucial at the time of design to consider not only the vibration of all machines individually, but also interaction between them as a system to reduce the vibration and noise must be taken into consideration. Vibration damping properties can reduce the operation costs and underwater radiation noise, and it's more practicable in 4-stroke engines than 2-stroke engines due to their size and weight, and can reduce underwater radiation noise by 10 decibel. Operational measures should not be underestimated in order to reduce underwater noise for both new and existing vessels. In this study, we categorize the operational measures to 6 subcategories. Ship's hull and propeller cleaning and maintenance. Marine fouling can significantly increase resistance, disrupting the smooth flow to the propeller and leading to higher fuel consumption and underwater radiation noise from vessel. Employing appropriate hull cleaning, regular hull cleaning, and proper maintenance removes marine biofouling, enhances efficiency, and reduces emissions up to 2 decibel. Optimize ships handling. Effective ships handling, along with consideration for design speed and trim, can lead the improvement in efficiency and a reduction in cavitation occurrence. A speed reduction for fixed pitch propeller, cavitation and machinery noise, which vary based on speed. 20% reduction in speed can lead to 30 to 35% less fuel consumption. In addition, 10% reduction in speed is predicted to yield a significant 40% drop in sound energy from global shipping. Applying just-in-time expected reduction of fuel consumption and greenhouse gas emissions ranging from 14 to 23%. Just-in-time shows the potential for an even more substantial 45% decrease in sound energy. However, it needs cooperation among stakeholders and development of sharing benefit policy among stakeholders. Passage planning, power demand, and weather routing. Passage planning, including weather routing, helps reduce resistance, lower engine load, and improve overall energy efficiency, ultimately resulting in underwater radiation noise reduction. Weather routing strategy can elevate vessel energy efficiency up to 5%, especially for vessels equipped with wind propulsion systems like rotor sail, which demonstrate the highest benefit. Underwater radiation noise from commercial vessels is a complex phenomenon. To overcome interrelated barriers in reduction of underwater radiation noise from commercial vessels, a systematic approach must be taken into consideration. It means not only technology and operational measures must be considered, but also the related environmental and social context, such as human factor, economic aspects, policy and regulation, must be taken into account. To reduce underwater noise from commercial vessels, single-dimensional thinking must be replaced with multidimensional one. In addition, the researchers and scientists from various disciplines must break their silos and consider appropriate transdisciplinary approach to create a new methodology, ideas, beliefs, and interests to overcome on the barriers in reduction of underwater radiation noise from commercial vessels. In conclusion, transition from single-dimensional to multidimensional thinking is essential for reducing underwater radiation noise from commercial vessels. Designing and developing underwater radiation noise management plan requires a holistic, systematic, and transdisciplinary approach. Considering trade-off in propulsion design between energy efficiency and underwater radiation noise reduction, acknowledging contradiction in propeller efficiency enhancement and underwater radiation noise reduction, highlighting synergy between underwater radiation noise reduction and improved energy efficiency is pivotal, and there is synergy among energy efficiency measures and in reduction of underwater radiation noise from commercial vessels. Measures like propulsion improving device, energy saving device, wind propulsion, and air lubrication system enhance energy efficiency, reduce air emissions, and underwater radiation noise. Slow steaming is crucial for meeting IMO's greenhouse gas strategy and underwater radiation noise reduction with varying thresholds based on vessel type and size. Collaboration among stakeholders is key to overcoming split incentives in underwater radiation noise reduction and energy efficiency improvement. Ports play a pivotal role in mitigation underwater radiation noise and air emissions from ships within port limits by incorporating underwater radiation noise management plan that encompasses various measures, including incentive initiatives. Thank you very much for your attention. If there is any question, I would be happy to answer.
Thanks, Vahid. I think we dropped you just for a second at the end there, but I'm sure we'll come back to those points. And one of the things, just for to let everyone know, we will share all of these presentations along with the video tomorrow, so you'll get those presentations. So if any of the detail you wanted, it's going to be there. And I think what was really interesting from what you were talking about is those payback periods. You know, it's a win-win, and then some of those payback periods could even be sort of 4 months, or depending on technical operational arrangements. So hopefully that's given the audience a bit of an overview of what are those, what are the issues, what are the regulations, and what can be done. But we do have questions coming in, and I remind everyone to, if you do have questions, put them into the chat function, and we'll get through as many as we can. And one we've had in is relating, I guess, back to the early point, Chris, about you were talking about sort of benchmarking and baselining the sort of the noise signature of a ship. And the question is, how do you do that? What's the best way to go about that for a vessel in service at the moment? And where is the best way to go?
The guidelines, they're very pragmatic, and they provide the option of doing it by measurement. And the normal way of doing that is with underwater hydrophones. The quiet ship class notation is provided by DMV, Bureau Veritas, etc. They provide guidance on how this can be done. And I know IACS at the moment, the International Association of Classification Societies, is trying to harmonise the approaches taken by the different classification societies to try and find a uniform approach to measurement of underwater radiated noise, for example, during ship trials. But the guidelines also allow or enable ship owners to baseline noise measurements by prediction through numerical analysis using techniques such as computational fluid dynamics. So it can be a desktop exercise. It doesn't necessarily need to be physical measurements, although certainly physical measurements with hydrophones is the best way. But it doesn't have to be. You know, it can be calculated. There is ongoing research for other methods. Certain groups are looking at onboard measurement of noise. Instead of having a separate hydrophone detached from the ship, keep the measurements on board the ship. It's not straightforward to do that, of course, because what you're really interested in is what the marine life experience is, which is the sound outside of the ship. But yeah, that's some ongoing research. Other groups are looking at hydrophones deployed by drones. You know, the idea that you can deploy a drone with deploy a hydrophone with a drone. The drone sits on the water, floats on the water while the hydrophone's working, and then when the measurements are complete, the hydrophone is lifted clear by the drone.
So there's a lot of things happening. A lot of things can be done. Our classification societies are working to try and bring everything together. So it's a moving piece, but CLASS can help guide ship owners as well in those conversations. So that's really helpful. Thank you. There was an earlier question, and a lot of what we've been talking about is the relationship with the energy efficiency measures and the shorter term operational requirements and the benefits and the win-wins. And there was a question, I don't know whether this has actually been thought through yet, in terms of, you know, what are the synergies between URN and GHG if zero emission fuels are being used? And I guess that's still a very nascent piece. I don't know, Bahedi, if any of the sort of research that you've been looking at in these new technologies have had any outcomes yet.
Yeah, thank you very much. Sorry, it's an interesting question. If we want to link, I mean, that reduction of underwater noise with IMO greenhouse gas emissions, as you know, there is a workshop will be held on 18 and 19 at the IMO headquarters. It will be discussed in more detail there. However, if I want to answer to this question, I would like to flash back to the IMO revised greenhouse gas strategy. IMO, as a regulatory body of international shipping, would like to reduce greenhouse gas emissions and meet zero emission by 2050. First of all, reducing carbon intensity by improving energy efficiency, and as well as a reduction of carbon intensity 40% by 2030, and consider two intercheckpoint 2030 and 2040 to be sure that we are in line. And also the most important thing I believe that is that fostering using zero emission technologies as well as fuel and energy. 5 to 10% of the energy and the fuel should be zero emission or near zero emissions fuel. If we look back at how we can achieve to zero emission by 2050, around 2050, the exact phrase is around and close to 2050. We have alternative fuel option. We have a speed reduction, improve energy efficiency and logistics. When we look at the alternative fuel, it cannot play a crucial role before 2030. It has a minor role. However, it picks up after 2030 and become dominant after 2040. And it predicted that contribute around 60% reduction of greenhouse gas emission by 2050. Meanwhile, a speed reduction, integration with just-in-time, and improving energy efficiency play a crucial role. It's predicted that they can contribute around 30% in reduction of greenhouse gas emissions by 2050. I would like to highlight that by considering CII requirement and EXI requirement, it is predicted that around 10,000 vessels decommissioned by next 3 years. 30% of vessels has the average vessel of container vessel, bulk, and tankers, which are contribute 75% of underwater noise, have the average age is more than 15 years, as well as it's predicted that this type of the vessel be classified to D, ranking D and E based on CII requirements. So speed reduction can play a crucial role as a low-hanging fruit. I mean, that to comply with CII requirement, and it is also effective for reduction underwater noise for fixed pitch propeller. The other option which we have, improving energy efficiency, I believe that wind propulsion system play a crucial role. It can accelerate, and we will see next decade more vessels that using the wind propulsion system, they can improve 5 to 30%, depends on type of the technology, improving energy efficiency. And one study shows that around 48% reduction of greenhouse gas emissions by 2030 is achievable through using alternative fuel, wind propulsion system, and the speed reduction and contribution of wind propulsion system was 25%. The other system is air lubrication system. 5 to 15% can improve energy efficiency. That can play a crucial role. The low-hanging fruits, the other is energy-saving devices, propulsion improving devices, hull cleaning, and also, as I mentioned, just-in-time play a crucial role. If you look at the package and consider the CII and EXI equation, you can see that although there is some contradiction exists for improving energy efficiency and reducing underwater noise, for example, the blade area for the propeller, that we have to consider trade-off between efficiency and underwater noise, there is synergy exists in improving energy efficiency and reduction of underwater noise without even burden additional costs for the ship owners. It means that if they choose correctly the measures, technical and operational measures for improving energy efficiency and comply with greenhouse gas regulations and rules, they can also achieve the reduction of underwater noise. So it's very important that we link these two factors with each other.
Okay, thank you. So I think that there's also that point of, now let's think about this now as we build, and Brett, in your earlier point in your presentation about breaking down silos and not thinking in, how do we do win-wins effectively. Yeah. And actually, there was another question in the chat, more specifically about and it's probably on the sort of URN reduces the lower speeds for ships with fixed propellers, but what are the options for adjustable pitch propellers? Because I think there was Chris, you highlighted that may not be as effective as other measures. So are there options for those who have got those technologies?
Yeah, the reducing speed with controller pitch propellers, it does tend to increase the noise from the propeller. But about 30% of the world fleet operates with controllable pitch. 2/3 operates with fixed pitch. And the fixed pitch propellers tend to be on the larger ships, bulk carriers, tankers, container ships, etc. The controllable pitch tends to be on the smaller vessels which need maneuverability, say shuttle tankers, harbour tugs, ferries coming in and out of port frequently. So the amount of sound energy they produce is significantly less, partly because the number of vessels is smaller, but also because the size of the vessels is smaller. There is also, we also have to consider that because some of these vessels are relatively small, the ones with controllable pitch propellers, they may fall below the limit for what we call the EEXI regulation, Energy Efficiency Design Index for existing ships, and EEDI, the equivalent for new ships. So they may not even need to slow down. If they're below that regulatory threshold, the regulation may not affect them, and they may not need to slow down. I think it's not as big an issue as you may think, partly because of the number of vessels and the size of them.
Thanks, Chris. No, that's a helpful clarification, I think, because just to move forward. And there was actually a question around, another clarification question around the URM management plan. Is it compulsory, and should it be available on board the vessels?
The guidelines are not mandatory, they're not compulsory. But I think it would be advisable to have the plan on board. There would be aspects of it that relate to the operation of the ship. So it would be advisable for it to be available to the crew, but it's at this stage, it's not mandatory. At ICS, we're encouraging ship owners to adopt the guidelines, use the guidelines. We see very significant synergy between the greenhouse gas reduction measures and noise reduction. And with sensible choices on the selection of energy efficiency measures, we think it should be pretty straightforward for ship owners to achieve significant noise reductions. And the noise management plan plays a role in that, setting the objectives for the noise reduction, possibly setting targets, and recording the baseline initially for, say, for an existing ship. You would seek to record the initial baseline noise, and then after doing the modifications, do the measurements again, or as we said earlier, you could use a predictive technique, a numerical technique, so you can see the difference. And at ICS, we would very, very much like to receive feedback from ship owners that go through that process. We'd like to learn how effective the guidelines are and what are the sound reductions that ship owners are achieving. That would be very useful for us to feed back to IMO to learn from that.
Thanks, Chris, and hopefully that's clarified for the audience there. And there was a question here specifically for Vahid. Could you elaborate more about the cooperation amongst stakeholders in conjunction to the just-in-time operation? Because we've all seen recently the issues around ports sitting outside. So how can we make that work in practice to have those both win-wins in terms of delivery, reduction of fuel, and also reduction of noise?
Yeah, thank you very much for a good question. As highlighted, I mean that because of the age of the vessel and complying with CII, speed reduction is one of the measures can be taken into consideration. And however, speed reduction, there are some criticisms and problem exist regarding speed reduction, that losing the capacity of the trade and maybe introducing another additional vessels to the fleet that maybe has a negative impact in increasing greenhouse gas emissions. However, by considering just in time, we can overcome to this barrier. When you have considered just in time, probably it will means that when the cargo is ready, you will adjust your ETA that to be away from anchorage, and also so when you're reducing the speed, it has a cubic relation, the power has a cubic relation with speed, and significantly you can reduce the fuel, and you can arrive on time with cargo is ready and be at the port without any delay and or any anchorage. So it can improve efficiency, and the study shows that depends on type of the vessels and the trade, 14 to 20% can improve energy efficiency. At the same time, when you're reducing the speed for fixed pitch propeller, of course, you can reduce underwater radiation noise. And as highlighted, 45%, one of the studies shows that around 45% energy source noise energy can be reduced from the ship. In the meantime, we have to consider that one of the problems which exists about the speed reduction is unfair distribution of the benefits among the stakeholders. By considering appropriate policy measures like fair sharing of benefits among the stakeholders in the charter parties, we can overcome to this barrier as well.
Okay, thank you. There's I think the colleagues at VIMCO are working on some of those activities as well. So hopefully, again, breaking down those silos, we can have a win-win operation. We've still got quite a lot of questions on the chat, and I think what we'll have to do is probably reply to some of the people afterwards, because I don't think we're going to have time to get through everyone at the moment. There's a, oh gosh, trying to pick where we go to now. There's a, let me try and clump maybe one or two. That some of the air lubricated systems that you talked about, Vahid, and some of the wind propulsion, obviously important. Are the numbers that you were quoting in off of real experiences, or were they predicted? Yeah, just to give some clarity on that. And then maybe Chris, I'll come to you with a question about incentives, because Vahid, was talk about incentives that were provided in Vancouver and other parts. Now, are there other elements of incentives that are out there, and also financial support? What are banks thinking about these kind of things? I'm trying to clump a couple of questions. So maybe Vahid, if I talk to you first, and then Chris, and then we'll probably have to wrap it up.
Yeah, about the percentage for improving energy efficiency measures. This is the thing that the companies claim, and they consider. I mean, that during the sea trial or during the lab exists in this regards. One of the issues, especially for underwater radiation noise, is reliability and is that effectiveness of the measures. So I think that we have to focus more and elaborate more about this effectiveness. These are the things that the references, I mean, that the companies and the references which has been highlighted, that they can achieve energy efficiency and in reduction of underwater noise. However, it needs more research and study in this regard.
No, that's helpful. I guess that's also part of, I know from underwater radiated noise, but in other areas, that's one of the things, Chris, you're looking for in terms of feedback from members on, the real world examples, because that's a valuable tool. Yeah, maybe hand over to you then, Chris, on that incentive. Do we need other incentives, or is it that we, there are win-wins already in here?
So far, we've seen relatively few examples of incentive schemes, and the only ones I'm aware of are the ones we mentioned in the presentation, relating to port fees. But we've seen systems, incentive schemes for greenhouse gas, like Poseidon principles, etc. So it may be possible for stakeholders such as the financial institutions, insurers, to run with this and consider giving some incentivization to the industry to move this way as well. But it's early days yet, and at ICS we see part of our role as not only raising awareness within ship owners of the new guidelines and the opportunities they present, but also the wider stakeholders. So yeah, early days, but we hope that mechanisms and ideas will be forthcoming.
Brilliant. Thanks, Chris. And I think that point around feedback and is important. So I think as we come to a conclusion, I just want to maybe hand back to Vahid and then Chris to sort of summarize. We've heard an awful lot. Those presentations are very rich in detail, and as I say, we'll send that to everyone on the call, and hopefully be able to answer some of the other questions in the chat as well. So get that back to everyone. But what are the takeaways that you would want the audience here to really grab from that? Well, you always say the three top things that you want people to take away from this. So maybe Vahid to start with, and then I'll go to Chris for that.
Yeah, thank you, Stuart. Yeah, to wrap up and for conclusion, I would like to say that underwater radiation noise is a complex phenomenon, and many stakeholders are engaged within. So we need a holistic, systematic, and transdisciplinary approach. We have not to focus only on technical and operational measures. We have to consider social aspects, human factors, economic aspects, and also policy and regulation in this regard. And we were talking about systematic. We have to look at different perspectives to the issue and consider the priorities of different stakeholders. And these stakeholders, because they have a different priorities, the silos between the different disciplines must be break, and we have to consider transdisciplinary approach to have the new perspective to underwater noise, new methodology, new approach for reduction of underwater noise from commercial vessels. The second thing is that collaboration is very important. Collaboration among stakeholders is crucial, especially between port and shipyards, and as well as other stakeholders, that they can play a crucial role to accelerate reduction of underwater noise. And in the last thing, I would like to say that, again, although some contradiction exists in improving energy efficiency and a reduction of underwater noise, there are many measures that can improve both energy efficiency and reduction of underwater noise at the same time, this does not cost any additional cost and burden additional costs for the ship owner for reduction of underwater noise. When they are complying with IMO greenhouse gas strategy, if they choose the appropriate measures, they can also enjoy from reduction of underwater noise. And I believe that in future we can see more regulation and incentive measures in different parts of the world, and they can enjoy from these incentive measures. And even in the short medium term, I believe that in some sensitive area, maybe we have the polluter pay principle, so in advance they can enjoy from these benefits, and considering underwater radiation noise within their sustainability domain can act as a brand for them and have a competitive advantage in the competitive market in the competitive shipping market. Yeah, thank you.
Thanks, Fahid. That's a good way of bringing it back, and certainly something I've taken away on the sort of opportunity there. Chris, if you the last.
Yeah, thanks, Stuart. I feel very encouraged and optimistic about the present situation in relation to the very significant synergy that is apparent between the greenhouse gas mitigation measures, the energy efficiency measures, and reduction of underwater radiated noise. When you consider the large list of energy efficiency measures and how many of those reduce noise, the majority do. You know, the overlap is like this. There's very, very few energy efficiency measures which drive up noise. So yeah, it's a complicated subject, but one way which perhaps makes it simpler is to focus in on those measures which make noise worse and avoid those. That's a very short list. And as I was explaining in the presentation, the only ones that I am aware of are the optimization of the blade area ratio of the propeller and slow running of controllable pitch propellers. Now, if anyone listening in knows of any others, I'd be very happy to hear. But in terms of making it a more digestible subject for ship owners, it's probably easier to focus on the efficiency measures which drive up noise and avoid those. Pretty much everything else, it will improve noise, it will reduce noise. Thanks, Jim.
Yeah, no, I think that's, you know, there are win-wins all the way down the line, aren't there? And you know, benchmark it at the beginning. If you don't what you don't measure, you can't show that you're making some success with. But there are small incremental steps, whether it's ship design, operational, that actually can have a benefit in terms of reduced amount of fuel used, reduced noise. So hopefully that's whetted the appetite of our audience. Obviously there'll be more coming down the line, and we'll help to try and articulate that. Please provide information back to Chris and the team here so that we can capture some of that information. And we'll certainly be keeping on with this. So hopefully everyone's enjoyed I found this a useful and valuable session, and we will be back in touch with colleagues later. Thanks very much indeed for your attention, everyone. And thanks for both Fahid and Chris for their presentations.
Thank you.
Thank you. Bye-bye.